Hi everybody, it's Saturday, February 1st, 2025. This is your Lecture 9. Before we start, I'd like you to make sure a couple of things. First, make sure you're comfortable. This is going to be a long one. Second, have paper and pencil at hand and have your calculator ready. I'm going to ask you to do some calculation. So as we go through the video, at certain points, I'm going to ask you to pause and to perform a calculation or answer a question. So have your paper and pencil ready for that. While you're getting settled, let me just remind you that you have a quiz coming up next week. So it starts on Thursday at noon. It's going to close Saturday just before midnight. The topics of the quiz are a little bit different than what I had thought. So here's what they are. There's going to be a 2-sample t-test, a paired t-test, and for both scenarios, confidence intervals. So this is the material you need to be ready for. So because this is a video lecture, meaning I have more time than normal, I'm actually going to give you some extra content. So in this video, we're going to start with Quiz 2 review material. I'm going to review both the 2-sample t-test and the paired t-test. After we do that, I'm going to give you the new stuff, and that's going to be the chi-squared independence test. This is the third and final chi-squared model that we're covering in the course. So far, you've learned the chi-squared goodness of fit test and the chi-squared homogeneity test. So we'll be hitting the independence test later on in this video. So let's start with a scenario which probably looks familiar to you. Here, we're asking, is the mean time before burnout for light bulbs produced in factory A the same as that for factory B? To find out, a random sample of light bulbs was taken from each factory. So in this scenario, in this case, for this scenario, I'm going to give you data. And with this data, we're going to calculate a 98% confidence interval for the difference between population means. So before that, let's just quickly check conditions. Do we have independence within samples? Yes, both samples are random. Do we have independence between samples? Also yes. The populations are from different factories, and so it's reasonable to assume the samples from each of those populations, those samples are independent of each other. Are our samples large enough? Well, yeah, both samples are greater than 40, and therefore we can appeal to the central limit theorem, and we can approximate our test statistic using a t-distribution. So here's our information. There's one more piece of information I need to give you. Do you remember what that is? Whenever you're faced with a 2-sample t-test, we need to tell you what the degrees of freedom are. In this case, the degrees of freedom are 141, or is 141? Yeah, whichever. It's 141. Okay, now look at the chalkboard at the bottom of the screen. There, I'm going to write down the formula for calculating this confidence interval. What I challenge you to do right now is, without looking at your notes, see how much you can remember. Try to write down the formula for the confidence interval without looking. Just pause the video, just spend a few minutes, try to remember, just challenge yourself. You might remember more than you think. So give that a try, and then once you're satisfied, resume the video. So, our confidence interval always has the same form. There's a point estimate plus or minus a margin of error. Furthermore, the margin of error is always a critical value times a measure of uncertainty. In this case, the point statistic for the difference between population means is simply the difference between sample means. The critical value comes from a t-table for 98%. And the measure of uncertainty is the standard error of y1 bar minus y2 bar. So continuing with the calculation, let's start with the hard part. Let's calculate the standard error. Just want to remind you again that in terms of calculations, this one is the most complicated one you'll see. It gets complicated, maybe more tedious than complicated, but it can be tedious. And so you need to practice it a little bit so that you can do the calculation efficiently and without error. So I'd like you to pause the video now and perform the calculation. Calculate the standard error of y1 bar minus y2 bar. Continue the video once you've completed the calculation. Okay, so plugging in values, you see that we have two fractions. On the top of each fraction, you can see we have the sample standard deviation, so 92 for the first sample and 106 for the second sample. We need to square those values, and each one is divided by its corresponding sample size. In the end, you take a square root. Now, however you do this calculation, make sure you are able to get this answer, 16.1820. What do we need next? Now that we have our measure of uncertainty, we need to look up, what is it? We need to look up the critical value for our confidence interval. So we'll go to a t-table. Degrees of freedom is 141. So take a few seconds, look at this table, and pick out the critical value for this 98% confidence interval. Degrees of freedom is 141, and so we're going to use 140. 98% confidence interval, you can see the critical value is 2.353. So what do we have so far? We have our critical value, and we have our measure of uncertainty. Starting from here, pause the video and go ahead and complete the calculation. Calculate the lower and upper bound of this confidence interval. Pause the video now. So let's see if we got the same answer. So the difference between the sample means is, let's see, it's 1,327 minus 1,305. So that's just 22. We can calculate the margin of error, 38.0762. And now 22 plus or minus that margin of error gives us a lower bound and an upper bound. And here we have our confidence interval. So what do we do next? We need to make our interpretation. So I'm going to remind you the parts of the interpretation. Now, probably on the quiz, any question regarding interpretation is going to be either fill in the blank or just selecting from multiple choice. But when you're writing the midterm and final, it's going to be a long answer. So just to remind you what I want to see, you're going to mention the conditions for the central limit theorem to apply. You're going to mention the level of confidence. You're going to say something about the parameter of interest with respect to this interval. And then you're going to tell me what you can infer about the parameter of interest from the interval. So here, pause the video, take a good 5 minutes, write down your best interpretation of this interval, and then we'll see what you got. So pause the video now, please. So here we are. We start with, since the conditions for the central limit theorem are in place, we are 98% confident that the difference between the population mean burnout times for the two factories, in this case it was factory A minus factory B, is between minus 16.08 hours and 60.08 hours. Since 0 is in the interval, we have no evidence at the 98% confidence level that the population means are different. That's 5 points right there. Excuse me. I feel like I want to ask, is there any questions? But I suppose there's no point in asking that. So I'm just going to continue. What else can we do? Well, that's the confidence interval part for a two sample. When you have two samples and you're comparing two population means. Now let's turn to the hypothesis test. So suppose we want to conduct a hypothesis test at the 2% level of significance. So our hypotheses are the population mean values are the same, and the alternative is that they are not the same, or in other words, they are different. So it's a two-tailed test. This is a sketch of the distribution of our test statistic, assuming the null hypothesis is true. What I'd like you to do is take a moment, just sketching on your notepad, sketch this distribution, and then put in the region where you would reject the null hypothesis. In other words, look up the critical value and then draw the region for your decision rule where you're going to reject the null. Pause the video and take a moment to do that. So, it's a two-tailed test. We're looking for critical values that put 1% into each tail. If you look at the t-table, you will see that by approximation, the values are plus or minus 2.353. And so the region over which we would reject the null hypothesis is here marked in red. Our decision rule will just be we reject the null if the absolute value of our test statistic is bigger than 2.353, which is just a math way of saying we're going to reject if our test statistic falls in the red zone. Now, how did I know it was 2.353? Well, we're looking at the exact same table, the same degrees of freedom. The critical value is the same. So the point here is that constructing a 98% confidence interval is equivalent to conducting a two-tailed test at the 2% level of significance. So all we need to do is calculate our test statistic. So we already have our standard error. Here's the formula for a test statistic. Pause the video, complete the calculation. So there we go. How do we calculate our test statistic? We look at our point estimate that we got from the data. We compare that to what we would expect to see on average if the null was true, and divide by our measure of uncertainty. In this case, under the null hypothesis, mu1 minus mu2, the difference between the population means, that would be 0. So we put 0 there. So it's 22 minus 0 divided by standard error. We get a test statistic of 1.3895. So we do not reject the null hypothesis because the absolute value of our test statistic is less than 2.353. Yeah. Okay, I had a little interruption there, so I'm not sure if you're going to see that. I'll try to edit that out. But in any case, right, so where did we leave off? We just rejected, no, we failed to reject the null hypothesis because our test statistic is not in the red zone. Our test statistic is too small. Oh, there it is there. Okay. One thing I want to review here is basically, let me take the opportunity to review the concept of a p-value. Again, I know that the p-value concept is very difficult for a lot of students. So here I'm just going to review that again. So the idea is we're looking for the probability that the test statistic would be as far away or further from 0 than what we observed if the null is true. In other words, if we were to collect some more data and repeat the whole process and get a new test statistic, if the null is true, what's the probability that test statistic would be as far away as the one we just observed, as far away from 0? And so if this was an upper tail test, that p-value would just be the area on the right-hand side. But because it's a two-tailed test, we have to look in both directions. And so it's both of those areas added together. So how do we estimate those? Well, we go to the t-table again. Again, we're looking at 140 degrees of freedom. We see our test statistic falls between these two numbers. And therefore, the p-value, looking at the two-tailed probability, falls between 10% and 20%. So the p-value is more than 10% but less than 20%. More than 10%, so we're not going to reject our null hypothesis at the 2% level of significance. Okay, so here we're looking at some Minitab output. And this is a typical question that you might see somewhere on a final or a midterm. Here, testing at the 2% level of significance, what can we conclude? So I'll pause the video here and write down something for the significance and for the strength of this test. So here, the significance, the p-value is greater than 2%, so we do not reject the null hypothesis. You can see the p-value, it's almost 10 times the level of significance. The p-value is pretty close to 20%, which is 10 times more than the level of significance. So there's no doubt at all that we're not going to reject. The strength of the evidence against the null hypothesis, there is no strength. It's zero strength. There is no evidence against the null hypothesis. And that's because we're here on our table with adjectives. What kind of error might we be making in this case? We failed to reject the null hypothesis, so what kind of error could we possibly be making? And that's a type 2 error. We might be making a false negative. Are we making a false negative? Who knows? But that's the only possible error we could be making. Okay, so that's the 2 sample t-test and confidence interval. Now let's move on to looking at the paired t-test. So here we're asking, does regular exercise improve school performance? To find out, test scores of randomly selected students who don't exercise were compared to test scores of those same students after 6 weeks of daily exercise. So you can see each student is being measured twice, and that makes it paired data. So let's say this is actually the data. So D is the difference. It's the test scores after doing the exercise for 6 weeks minus before. And we have a sample size, a sample mean, and a sample standard deviation. We're going to start by constructing a 95% confidence interval for the parameter of interest, which in this case is the population mean difference. So we'll check conditions quickly. Independence, yeah, it's a random sample. And large enough sample, yeah, the sample size is bigger than 40. So we're good to go ahead and use the center limit theorem and use a t-table. So here again, you can see the empty chalkboard. I would like to challenge you again to just take a pencil and paper, write down everything you can remember about the formula for calculating this confidence interval. Just pause the video, take a few minutes, write down as much as you can remember. So again, the confidence interval always has the same form. There's a point estimate plus or minus a margin of error, and the margin of error is just a critical value times a measure of uncertainty. So in this case, the point estimate is the mean difference from the data, and the critical value comes from a t-table. The measure of uncertainty is just the standard error of d bar. So here, go ahead and do the calculation. This one should be quite straightforward. Calculate the standard error of the mean difference. So let's see if we got the same answer. Here, 35 is the standard deviation of the sample, of the differences, divided by the square root of 83. We get 3.8417. Now let's look up the critical value. Remembering that the degrees of freedom is 82, just have a look at the table and pick out the critical value for our confidence interval. So we're at 82 degrees of freedom. By approximation, we're going to use 75. It's a 95% interval, so our critical value is 1.992. So we have everything we need to calculate this interval. We have our sample mean, we have the standard error, we have our critical value. Go ahead and complete the calculation. Just pause the video here. Calculate the upper and lower bounds. So, doing this calculation, we get a lower bound of 18.3473, an upper bound of 34.6527. Next, let's do the interpretation. So just to remind you of the context, we're asking, does regular exercise improve school performance? We're looking at the difference between, for a student, let me back up. We're looking at test scores for a student after 6 weeks of exercising and comparing that to their test score before they started the exercise. So it's after minus before. This is our confidence interval. You're going to write down something about the conditions, the confidence, the parameter of interest, and state what can be inferred from this interval. So pause the video, take a good 5 minutes, write down the best interpretation you can for this interval. Here's what I wrote. Since the conditions for the center limit theorem are in place, we are 95% confident that the population mean difference, that being test scores after 6 weeks of daily exercise minus test scores before, is between 18.35 and 34.65 points. Since 0 is not in the interval, we have evidence at the 95% confidence level that the population mean difference is not 0. And since the interval is positive, we have evidence that daily exercise improves test scores on average. Okay, now we're going to look at the other side of the inferential coin. We're going to do the hypothesis test, 5% level of significance. Here, upper tail test, we're looking to see whether test scores improve, whether exercise improves test scores or not. So we're going to do an upper tail test. So what I want you to do here, you're going to pause the video, make a sketch of the distribution of your test statistic, and mark in the region over which you would reject a null. Pause the video now. So here's the distribution of our test statistic. The sample size was 83, and so we have a t-distribution with 82 degrees of freedom. We're looking for a critical value that puts 5% in the upper tail because it's an upper tail test conducted at 5%. That turns out to be 1.665. So there's our red zone. If our test statistic falls in the red, we're going to reject a null. So we can say we're going to reject if our test statistic is bigger than that critical value. And just to be sure, how did I get that critical value? We're looking at 82 degrees of freedom. The best we can approximate is 75. We want to put 5% into the upper tail. So we're looking at the one tail probability, 5%, critical value 1.665. So you can guess what you're going to do next. You're going to calculate your test statistic. So pause the video, take a moment, and calculate that test statistic. So the sample mean was 26. The mean under the null hypothesis is 0, and the standard error is 3.8417. So we get a value of 6.7678. So what do we say? Well, we're going to reject the null because the test statistic is greater than the critical value. In other words, our test statistic falls in the red zone. Let's estimate the p-value. So again, working with 75 degrees of freedom, you can see the test statistic is off the chart to the right. So if our test statistic was 2.643, the upper tail area would be 0.005. But our test statistic is much bigger than that, so the upper tail area is even less than 0.005. The p-value is less than 0.005. Okay, next, pause the video and write down what you want to say about the significance and the strength for this scenario. So here the p-value is less than 0.05 or 5%, so we can reject the null hypothesis and conclude that the population mean difference is greater than 0. For strength, you can see the p-value is very, very small, and so there's very strong evidence against the null hypothesis. Very strong evidence because we are in this region. And finally, what kind of error might we be making? We did reject the null hypothesis, so we might be making type 1 error, false positive. Okay, now we move on to the new stuff. Continuing with chapter 22. We're going to start now with the chi-squared independence test. Now here, you're given counts for various combinations of two categorical variables. Now those are going to be in a contingency table, and you're going to be asked whether the two categorical variables are associated or dependent. The counts are drawn from one population. The null hypothesis is that the two categorical variables are independent. So in summary, for this test, we have two categorical variables and the sample is drawn from one population. And so here's a scenario. Let's just pretend that we interviewed 150 randomly selected MSVU students. And we're going to ask them about two things. First, we're going to ask, do you like sports or not? So that's one categorical variable. And then we're going to ask, do you like to read or not? That's the second categorical variable. So you see we have a sample from one population, two categorical variables. We're going to ask the question, are these preferences, the reading preferences and the sports preferences, are they associated or dependent? And we're going to test at the 2.5% level of significance. So in this case, the chi-squared independence test, the null hypothesis is that the two categorical variables are independent. So in this case, the null is that the reading and sports preferences are independent of each other. The alternative is that they are not independent, or to put it another way, it is that the two categorical variables are dependent. So the null, independent, the alternative, dependent. Now, as usual, as you've seen with the goodness of fit test and with the homogeneity test, we have to calculate a chi-squared test statistic. And so before we do that, let's figure out what the degrees of freedom is. Now, the good news is, just like the homogeneity test, where you were given a contingency table, here too, you're given a contingency table, and so the degrees of freedom is calculated in the same way. It's just the number of rows minus 1 times the number of columns minus 1. Now, the only thing you have to remember is that when you're given the table like you're seeing here, where the marginals are filled in, the marginal totals, when you count rows and columns, you're ignoring those margins. And so it's just the actual counts that you look at. So in this case, there's two rows corresponding to whether you like sports or not like sports, so the two levels of that categorical variable. And likewise, there's two columns for the other categorical variable. So the degrees of freedom in this case is in fact 1 degree of freedom. So now we can look at a chi-squared table and figure out what our critical value would be for a 2.5% test. 1 degree of freedom, we want 2.5% in that upper tail, so our critical value is 5.024. So that means our decision rule is just this. We will reject the null hypothesis at the 2.5% level of significance if our test statistic is greater than the critical value, 5.024. So now all we have to do is calculate that test statistic. And so there's two steps, of course. First, we have to calculate what we would expect to see for each of these 4 contingencies if the null hypothesis was true. In other words, we need the expected counts. And just remember the big idea. We're going to compare what we observed, the counts that we observed, with the counts that we would expect to see if the null is true. The bigger that statistical distance, the less likely it is that the null is true. That statistical distance is measured by the chi-squared statistic. So, starting with calculating expected values. Turns out that the expected counts are calculated here the same way that they were calculated for the homogeneity test. However, they're calculated in this way, in this scenario, for a different reason, and I want to explain what that reason is. So the first thing to realize is that these marginal distributions that you see in bold here on the table, we can use those to calculate probabilities, and those probabilities provide the best estimates for the population distribution of each of these preferences. So for example, if we're looking at likes sports versus doesn't like sports, you can see that from the data, the probability that one of these 150 students likes sports, it's just 60 over 150, so it's 0.4. And of course, the probability that they don't like sports is just 1 minus that number. So 0.4 and 0.6 provide our best estimates for the corresponding population probabilities. Likewise, for the other categorical variable, We look at 45 over 150. That gives us our best estimate of the population probability that an MSVU student likes to read. In this case, 30%. And likewise, for not liking to read is 1 minus that, it's 70%. So again, these marginal totals, we can convert them into proportions. Those give us our best estimate for the probabilities of each of these preferences. Now, here's the cool part. If we want to calculate an expected value, so for example, if we're looking at the first contingency where we observed 25 out of 150 students were in that first contingency, if we want to calculate the expected value, assuming that all is true, we just need to remember the product rule for independent events. So let me just put that in words. Remember that from 2208. If A is an event with some probability of happening, and B is another event with some probability of happening, if A and B are independent events, then the probability that A and B happen is just the product of their individual probabilities. And that's important because here, remember, we're testing under the null. Well, we're testing for dependencies. The null hypothesis assumes these two categorical variables are independent. And so our stance is always, let's start by assuming the null is true. So we're assuming independence, which means if we want to calculate the probability that one randomly selected person likes to read and likes sports, then that probability is just the product of those individual probabilities because we're assuming independence. And so we can calculate that and we come up with 0.12 or 12%. So if the null is true, we expect 12% of people at Mount St. Vincent University to like sports and like reading. So for our sample size of 150, 12% of 150 would give us the expectation for that contingency. So here it follows, given those probabilities, it follows that the expected number of those surveyed, those 150 people surveyed who like sports and like to read, is 18 people. And how come 18? Because we can take the probability that a person likes sports and likes reading, multiplied by the sample size. That gives us 18 students in total. So the expectation for that first cell is 18. Now, why did I go to the trouble to explaining this? Because I want to show you here the expected count for this first contingency marked in yellow. We're taking first 45 over 150. What is that? That's the probability that a person likes to read. We're multiplying that by 60 over 150. That's the probability that a person likes sports. Because we're assuming independence, the probability that a person likes to read and likes sports, it's just a product. And to get the expected counts for that contingency, we multiply by the total sample size. Now notice, two of those 150s cancel. What do we get left over? We get the column total divided by the grand total times the row total. So you see the formula for calculating expectations is the same here for the independence test as it was for the homogeneity test, but for different reasons. So I think that's neat. You don't need to ever explain that to anybody. In the end, you just need to know how to use this formula. But I know at least some of you are going to appreciate understanding why this formula is the one we use. Having said that, let's just get some practice using the formula. So we're calculating expectations. We did the first one already. So we took the column total, 45, divided by grand total, 150, multiplied by the row total, 60, we got 18. So for the first cell, the expected counts is 18. Pause the video and take a moment to calculate the expected counts for the next cell, for the next contingency marked in green here. Pause the video now and do the calculation. So for this contingency, you can see the column total is 105, the row total 60, grand total still 150. So we go column total divided by grand total times row total, we get 42. So here, the expected counts is 42. So pause the video again and do the next one. Right, so here, we take the column total, 45, divided by grand total, 150, times the corresponding row total, 90. We get a count of 27. And now do the last one. Just pause the video for a minute. Do the last calculation. And so here again, we have a column total of 105 divided by the grand total times a row total of 90. We get 63. So in the end now, we want to calculate the statistical distance between the observations on the left and the counts we would expect to see for each of these contingencies if the null is true. How do we do that? Well, it's convenient to just put our numbers in a table. So we have our observations in the first column, our expectations in the second column. Calculating that expectation, we use this formula. And what does the formula tell us to do? For each observation, we subtract what we would expect to see. That difference is called a deviance. We square the deviance and then divide again by expectation. So for example, in the first cell, we observed a count of 25. What we would expect to see on average if the null was true is 18. That deviance squared, divided by 18 again, gives us 2.722. So that's the contribution to the chi-squared statistic by the first observation. Whoops. Okay, so I want you to pause the video and calculate the second contribution to this chi-squared statistic. Pause the video and take a few minutes to do that calculation. Okay, here we observed 35. The expected count is 42. That difference, that deviance, you square it, divide again by the expectation, 42, you get 1.1667. Okay, go ahead now, pause the video again, do the next calculation. So here it was 20 minus 27 squared, divided by 27, 1.8148. Do the last calculation now. Pause the video, do the last calculation. Right, here the observed was 70. What we would expect to see on average if the null is true is only 63. We square that deviance, divide again by 63, we get 0.7778. So now we have the contribution made by each observation to this chi-squared statistic. What do we have to do? Next, we add them up. So I'm not going to make you do that. I'm sure that's something you can do easily. When you do add them up, you get a chi-squared statistic of 6.4815. So now here is an important statement. This is a statement that conveys the whole concept of the chi-squared test. And this concept holds for all three tests. Here I'm talking about this one in particular, but the same idea applies. So the chi-squared statistic is the sum of these individual contributions. It measures the statistical distance between what was observed and what we would expect to see on average in a sample of size 150, assuming the null is true. In this case, i.e. that the two categorical variables are independent. So if these categorical variables are independent, this gives us a measure of the distance between what's observed and what we would expect to see under that assumption. The bigger that distance, the less likely it is the null is true. Is that distance big enough to reject the null? Well, let's go back to our decision rule. Right, so we had already decided that if our test statistic is bigger than 5.024, we would reject the null, and so here the test statistic is greater than that number. Hence, we reject the null and conclude that in the population of MSVU students, sports preference and reading preference are dependent, or you could say not, or you could say associated. So they are dependent or associated at the 2.5% level of significance. Okay. Okay, we can estimate the p-value for this test. We're looking at 1 degree of freedom. Our test statistic falls between these two numbers, and so the p-value falls between 1% and 2.5%. So here we are. Of course, the p-value is less than 2.5% because we rejected the null at the 2.5% level of significance. So the p-value has got to be less than 2.5%. But it's also greater than 1%. So what do we say about the evidence? Well, maybe you can tell me. Take a moment now. Pause the video here. Write down what you should say about the significance and the strength of the test. So for significance, we say the p-value is less than 0.025. In fact, you can see it's quite a bit less. It's only 0.011. So we can reject the null and can conclude that the two categorical variables are independent. Oops. I meant to say dependent, didn't I? That's funny. Right. Okay, just to make absolute certain we all are on the same page. The null hypothesis is that the categorical variables are independent, and we based the calculation of the expected values, and therefore the chi-squared statistic, on that assumption of independence. We rejected the null, and so we must say that we have evidence that these two categorical variables are dependent or associated. Okay, yes, that's correct. That's what I had here. Okay, skipping ahead of this. There we go. Right, so we can conclude that the two categorical variables are dependent. And as far as the strength of the evidence, the strength of the evidence against the null hypothesis is only moderate. And that's because we're here on this table. Okay, so we're just about done. Let's see, what kind of error might we be making? We rejected the null hypothesis, so that means we could have made a false positive. That's possible. Let's look at some Minitab output. So on the left-hand side, you can see there's two chi-squared statistics. There's a Pearson and a likelihood ratio. Of course, you need to remember, we only really care about the Pearson one. That's the one on top. In this case, it doesn't matter that much because the p-values are the same, but the p-values aren't always the same. And certainly the test statistics in this case aren't the same. Let's just point out that the chi-squared statistic that we calculated agrees with what you see for the Pearson chi-squared statistic. And also what we concluded about the p-value is consistent with what we see here from Minitab. So that's all good. On the right-hand side, we see an example of the kind of table that you could well see on a midterm or final. And in this case, it's important to recognize which are the observed and which are the expected counts. So the observed counts are on top. The expected counts are underneath. Later in the course, we'll look at some other tables where you will also see for each observation and expectation a third number, which represents the contribution to the chi-squared statistic. We're going to see some of those in the next few classes. Let's look at the model assumptions. We have two categorical variables for an independence test, two categorical variables and samples drawn from a single population. It has to be a random sample, of course, and all expected counts must be 5 or more. And so looking here, we can see our expected counts indeed are all 5 or more. So that condition is satisfied. If one of these expectations was less than 5, then the test would be invalid. And just to provide some explanation, the reason the test would be invalid is because the distribution of the test statistic, this chi-squared, that chi-squared distribution is only an approximation. And the approximation is good under certain circumstances. That's why we have these conditions. If one of the expected counts is less than 5, then that approximation is no longer any good. The more data you have, the bigger the sample size, in general, the better that approximation. But it's just important to remember that when we say that the test statistic follows the chi-square distribution, that is still an approximation. And that approximation is no good if any of the expected counts are less than 5. And so finally, I want to sort of give you a brief summary of what we talked about so far with chi-square tests. Of course, you're going to see lots more examples in class. But for now, 3 things to remember. First, a goodness of fit test, you have one categorical variable and one population. So in a scenario, when you see there's only one categorical variable and only one population, it must be a goodness of fit test. Secondly, for a homogeneity test, you also have one categorical variable, but you have 2 or more populations. And finally, for the test we learned today, the independence test, you have 2 categorical variables this time, but only one population. So this is the only test with 2 categorical variables. That's how you recognize when you're facing an independence test. Okay, so we'll look at some examples in a few classes from now. I will give you scenarios, and you'll have to guess which of these models apply. So that's it. So I hope you learned something. I hope you enjoyed that. I wish you luck on your quiz this week. So I'm not seeing you on Tuesday. I may or may not see you on Thursday. I will let you know how that goes. I'm going to make a video for Thursday and have it ready just in case, but if I can show up, I will show up. Okay, so study well, and I'll see you next time I see you. Bye-bye.